0.0002 so that we get a common denominator?
No, no. At the moment, what you're trying to do there is what you have to do when you've got the more complicated series RLC circuit.
Ah, right.
At the moment, we've got a fairly simple circuit, so we're going to write an equation for IS.
Is that VS over ZS?
VS over ZS. So we've got a VS, which is 100 over S. And we've got ZS as 4 plus 1 over 0.3022 S. Remember that, Callum?
Yeah.
Yeah. We don't need to do any simplification on the impedance for this problem.
Yeah.
All right.
Yeah.
So now we've got a fraction. We've got a fraction over effectively, which is a fraction of a 1. So we can say that's equal to 100 over S times 1 over 4 plus 1 over 0.3022 S, like so. Yeah.
Yeah.
And then we multiply that out. So 100 times 1 is 100. Yeah. And we get here 4S. And then the S on the other part cancels out because we end up with S on top. And 0.3022 S on the bottom, so the two S's cancel out. You see that?
Yeah.
Mm-hmm.
So that will be plus S over 0.3022 S, but the two S's cancel out, so we end up with 1 over 0.0022, and the S is gone. All follow that?
Yeah.
Yeah.
Yeah. What do I need to do with that next?
You probably need to do something with that fraction on the bottom.
You need to divide them by 4, don't you?
Oh, I'm going to get us plan up now. Come on. Just pause the recording for a minute.
He said he was getting a laptop, so you might just have to download the Zoom app on
the
his
Zoom,
laptop.
yeah. Okay. So you can divide 3 by 4, so we get IS is equal to 25 over S plus, and that comes to 1136. Yeah.
Mm-hmm.
Okay. And that, if memory serves me rightly, looks like A over S plus B in the table. So we can transfer back. And the form is IT is equal to, I think that's A, which is 25 E to the minus 1136 T amps. Yeah.
Yeah.
Just check all your calculators. So what that's saying is this current starts off at 25 amps and falls exponentially towards 0. Yeah.
Yeah.
Does 25 amps initial current make sense? If we look at the circuit, initially we'll have 100 volts as we turn on, because there's no volts across the capacitor. We'll have 100 volts across the 4 ohm resistor. Therefore, the initial current is 25 amps. So it does make sense. Yeah.
Yeah. Yeah.
Okay. Right. Let's see how far you get with this one. So we got 150 microfarad capacitor.
That's a four.
In series with 6 ohms. And a step input, 50 volts. Yeah. Use Laplace transforms to find an expression for VC across the capacitor. Yeah. So if you really need to, you'll find an example like that in your notes. But make a start and see how far you get. What we have to do is equate the numerators. Do you remember doing that? Because the two denominators are equal, we must then be able to say that 50 is equal to I times 0.309 S plus 1, yeah, plus BS. Okay? And then, if we let S equals 0, so BS equals 0, 50 is equal to I times 0 plus 1. I equals 50. Agreed?
Mm-hmm.
Mm-hmm.
Yeah. And then what we do is let this expression that I is multiplied by, so we go let 0.0009 S plus 1 equals 0. And then rearrange that to find the new S. So 0.309 S equals minus 1. S equals minus 1 over 0.309, which equals whatever that equals when you put it in your calculator.
Minus 1,111.1.
1,111.
0.1.
Yeah, I'll leave it at 4 significant figures. Yeah.
Yeah.
So then we can say 50 is equal to 0 because hang on, we've got to let S equal X. I could run out of page so damn quick. That's right. So now we can say 50 is equal to, the A term has disappeared because we've set that other part equal to 0. So 50 is equal to minus 1111 B. Yeah. Therefore, B is equal to 50 over minus 1111, which equals I make it minus 0.0450.
Yeah.
Actually, that'd be that's near, and that would be 1 because if you look, calculate that's reoccurring after that. And that'll do anyway. Minus 0.045. So B equals minus 0.045. Yeah.
Yeah.
So now we can put those values for A and B back into the original equation we had before. So we can go, therefore, VC in S space is equal to 50 over S minus B, which is because that's A over S. B is minus 0.045 over 0.00009, wasn't it? Yeah.
Yeah.
S plus 1. Yeah.
Yeah.
Okay. Now we need to get we need to divide by 0.0009. This term, the right hand term, not the 50 over S. Leave that as it is. .045 divided by equals 50. Yeah.
Mm-hmm.
And then we got to divide, and then we end up with S here. Yeah.
Mm-hmm.
So, change colour, red. This bit looks like A over S, and this bit looks like A over S plus B. So we can now convert back. VC at time t is equal to A over S as a constant, so it's 50, yeah, minus 50 E, hang on, we divided 1 by .0009. 1,111. E to the minus 1111 t. Yeah.
Mm-hmm.
And then we got a common term there, so we can take that outside the brackets. 1 minus e to the minus 111 t volts. Yeah. And is that what we would expect for a capacitor charging? If we think about that, it's saying it's going to be an exponential rise to a limit of 50. It's going to go like that, with that being 50 volts over time. And that's what we would expect for the capacitor charging. Yeah.
Mm-hmm.
Okay. Right. The next problem, ramp voltage. So we're talking about a voltage that goes up over time at a rate of 0.5 volts per second. Yeah. It's applied to just a capacitor, 660 microfarads. So we've got a ramp voltage, 0.5 volts per second. So Vs here is 0.5 over s squared. I'll give you that start. Haven't got that one, see if you can work that one out.
So I guess Matt ain't making it then.
Well, yeah, I unfortunately I can't wait forever.
No.
As he said, so far what we've done is we've got Vs as 0.5 over s squared.
Times 0.0.
Over here. Zs is equal to 1 over 0.00066s. We put that into an expression for the current, 0.5 over s squared divided by 1 over 0.3066s. So we need to do that division by keeping the top fraction up the same way, turning this fraction up the other way, times 0.3066s over 1. Yep.
Mm-hmm. Then that'd be.
So 0.5 times 0.00066 is 0.00033, and half of 66 is 33. S on the top, and on the bottom, s squared. However, we can cross that out and cancel that s. So that's equal to 0.00033 over s. Where have you seen that before?
Is that the A over S?
Yeah. Looks like A over S. Therefore, I, T, is equal to 0.00033 amps equals 330 microamps. Constant current, which is what happens if you put a ramp into a capacitor. You get a constant current. Yeah.
Mm-hmm.
So that's correct. It's the answer. Simply, IT is 330 microamps. Back in the science in year 1, when we looked at how capacitors work, said if you keep charging at a constant rate, so you keep increasing, keep the current constant, the capacitor voltage will go up in a ramp. Yeah.
Right.
Okay.
Yeah.
So that's that one. Right. The next one is an inductor, 4.5 ohm, 22 millihenry, step voltage of 45. Use Laplace transforms to find the expression for the current. So I'm going to leave you to do that one for the time being. It is one that will require partial fractions. So you need to look initially to get the denominator looking like S times a bracketed term, so that you can write it in 2 partial fractions and solve it from there, a bit like you did the other one, except this one's for current. Okay?
Mm-hmm.
So we've got 4.5 ohms, 22 millihenries. A step voltage of 45 volts. Yeah. So Vs is 45 over S, and Zs is 4.5 plus 0.022 S. Yeah, I'll just give you a start.
Is this step into RL, Mike?
Yeah, it's step into RL, yeah. Minus 204, yeah?
Yeah.
Point.
Oh, 4.
5. We'll say 0.5, that'll do. Okay?
Mm-hmm.
So, what we can do then is say 45 is equal to, the A term disappeared because we set that term to 0, is B times minus 204.54. Yeah.
Yeah.
So B is equal to 45. I got minus 0.22. Yeah, minus 0.22.
Yeah.
Yeah.
That's what I've got.
So then we put A and B back into the two partial fractions, so we can go I of S is equal to A is 10 over S minus B 0.22 over 4.5 plus 0.022 S. Yeah.
Yeah. So would we divide that by 0.022
Yeah.
now?
Just the right hand fraction, not the 10 over S. So we've got 10 over S minus, and you should get 10 on the top. Yeah. And this is 204.5 plus S. This bit looks like A over S. This bit looks like A over S plus B. So we can transfer back. I T is equal to 10 minus 10 E to the minus 204.5 T. Yeah, which is 10, 1 minus E to the minus 204.5 T. Yeah.
Mm-hmm.
Which is a exponential rise to a limit, yeah, of 10 amps. If you look back at the circuit, yeah, when you initially turn on, the inductor is going to act like a short circuit. So you've got a current of 45 volts divided by 4.5 ohms is 10 amps initially. But then the back EMF in the inductor will limit. So once you hit steady state, you've got 45 volts across 4.5 ohms. But prior to that, you've got a back EMF forcing current back the other way. It's going to cause this hold up in the rise to its limit. Yeah? And that's what you would expect to step into LR. Okay?
Yeah.
Everybody else happy with that?
Mm-hmm.
Yeah.
These are just different examples to every different type of one we've already done in the preceding weeks. Yeah. So the next one on the list, and that'll be the last one today. We probably won't even get through the solution to this, but I'll get you started. 50 millihenry inductor in parallel with a 6 ohm resistor.
Oh my God.
parallel combination is then connected in series with a further resistor of 12 ohms. So let's draw the circuit. So we got a 50 millihenry inductor. In parallel with a 6 ohm resistor. And then that's in series with a 12 ohm resistor. And it's connected to a step voltage of, let's say, 96 volts. Yeah. So we've still got a ZS that is simply 96 over S. We need to be able to express the total impedance in one go for this problem. So we're looking at ZS being the 12 of the series resistor plus, now we need to do product over sum on these two in parallel. So the 50 millihenries is 0.05 S.
You times that by your 6.
Times 6 on the top.
Then you plus
and the bottom is 0.05 S plus 6 on the bottom. Yep. Then we multiply that out. Get ZS is equal to 12 plus 6 times 0.05 is
43.
Oh no, hang on, I ain't done that. Right. Divide by 0.05. Yeah. So if we do that, we end up with 12. Don't divide the 12 by 0.05. This will be 6S on the top and 120 plus S on the bottom. Yeah. Now we multiply 12 by 120 plus S over 120 plus S. That'll give this part and this part the same denominator. Yeah. So ZS is equal to 12 times 120 plus S over 120 plus S plus 6S over 120 plus S. So they've both got the same denominators. Yep. So then we can write this as 12 times 120 plus S plus 6s all over 120 plus s.
Mike, there's
So
something
I've
that's
got,
can you
yes, Callum.
just go back 2 steps? What the very top calculation on that page, where you divide by 0.05, where does the S go? Because you've still got an S on the top, 6s. Where does the S go for the 120?
That six divided. What you're doing, Callum, is dividing. So I've just got to change my colour to blue. What you're doing is dividing all of this bit, right, by 0.5. Yeah.
Yeah.
Mm-hmm.
So you end up with 6 divided by 0.05 is your 120. Yeah.
Right. Yeah.
And then 0.05s divided by 0.05s is just s. So you end up with 6s on the top and 120 plus s on the bottom.
Oh, I see. Yeah.
Yeah. I'll just change the order because that's the normal way around you'd write it. Yeah.
Yeah. Yeah. No problem.
Okay.
Yeah.
Sorry about that.
No, that's all right.
Yeah. Okay. You all right with that now?
Yeah. Yeah. It's just clicked. Yeah. It's fine.
Yeah. So then we can multiply out the brackets on this top line here. So we end up with 12 times 120, which is 1440. Yeah. Plus 12 times 6 is
22.
hang on, no, it's 12 times that is it's 12 times s is 12s plus 6s over 120 plus s. Yeah. And we can simplify that by saying that is 18s. All happy with that?
Mm-hmm.
Yeah. So I'll take that to a new page. So now we can write our expression for I. It is Vs over Zs. And that is 96 over S on the top. This 1440 plus 18s over 120 plus s on the bottom. Yep, all happy with that?
Yeah.
And then we can do that division by saying it's 96 over s times 120 plus s over 1440 plus s. Yeah. All right.
Mm-hmm.
And that equals 90 times 120 plus s over, 96 over s times 1440 plus s.
Where'd the 18 go? Mike. from that? Where you've rearranged
Me.
Oh, so still plus 18s.
That's me. It is, yeah, it is 18, yeah.
Right.
It's by deliberate mistake, Dan.
Just testing.
Remember them? Yeah, just testing, yeah. Let's tidy that 96 up as well. Yep. Okay.
Mm-hmm.
And that can be written as a partial fraction. So we can go 96 times 120 plus S over S 1440 plus 18S is equivalent to I over S plus B over 1440 plus 18S. Yep.
Mm-hmm.
Which is equivalent to I times this denominator, 1440 plus 18S, plus B times S, all over the common denominator. Yep. Happy?
Mm-hmm.
As you're ever going to be?
Mm-hmm.
Yeah.
Yeah.
So, new page for me. We can say equate numerators. Such that 96 times 120 plus S is equal to I 1440 plus 18S plus BS. Yep. And we let S equals 0, so the B term disappears. So if S equals 0, this becomes 96 times 120 is equal to I times 1440 plus, and if S is 0, 18S is 0. Yeah. That's 11520, I believe, is equal to 1440 I. I is equal to 11520 over 1440, and I've got 8. Just check that.
Yeah, I got 8.
8 exactly, yeah?
Mm.
So I is 8.
You'll be done in a sec. We've written this.
And then we've got to let 1440 plus 18S equals 0. Yeah?
Mm-hmm.
That means 18S is minus 1440. S is equal to minus 1440 over 18. I'll make that minus 80. Yeah.
Mm-hmm.
So 96 times 120 minus 80 is equal to minus 80b. That's 3840 is equal to minus 80b. B is equal to 3840 divided by minus 80 equals, I'll make that minus 48. Yeah. Right.
Mm-hmm.
A and B values back into partial fractions. We get IS is equal to 8, the value of A over S, minus 48, value of B, over 1440 plus 18S. So the last thing we need to do is divide the right-hand fraction by 18S to get S on its own. So we end up with 8 over S there. Sorry, not divided by 18S, divided by 18. Yeah.
Mm-hmm.
We end up with 8 over S minus 2 2/3. It's a better way to leave it than 2.667. All right, over 80 plus S. This bit looks like A over S. This bit looks like A over S plus B. Yeah, so we can transfer back. We get I T is equal to 8 minus 2 2/3 E to the minus 80 T. Yep.
Mm-hmm.
And what you've got there is, if you look back at the circuit, when you initially turn on, okay, you're going to have some resistance from the 12 ohms. But initially, 96 over 6 is going to flow through, is always going to flow through the 6 ohm resistor. Yeah?
Yeah.
Sorry, not 96, because initially, when you switch on, your total resistance is the 12 plus 6 is 18. So initially, you're going to get 96 over 18, 5 1/3 amps. Yeah.
Mm-hmm.
Mm-hmm.
Okay. And then, a minute, no. Initially, the inductor is going to act like a short circuit. So you're going to get 96 over 12. 8 amps. Yeah. So you're starting at 8 amps. Yeah. And then what's happening is you're rising up to, fallen and into, because as this initially that's like a short circuit. After that's like a short circuit. It does, I know what it does that. So it starts at this 2 2/3, yeah, and rises up to, so it starts at 5 minus 2 2/3. 3 2/3, sorry. Yeah. Anyway, that's what happened. It rises because once you get to the steady state, the inductor acts like a short circuit. So you just got 96/12. So that's your 8 amps.
Mm-hmm.
Yeah. Eventually, this bit here, the exponential bit, over time gets smaller and smaller. Yeah. So you're taking less and less off the 8 amps. So you start low and you rise up to 8 amps. Yeah.
Yeah.
Initially, this bit is worth, when t is 0, this bit is worth 2 2/3. So your initial current is going to be 8 minus 2 2/3, which is 5 1/3. So you're going to start here at 5 1/3 amps and rise up to, and that 5 1/3 amps came from 96/18, didn't it? Yeah. See that?
Yeah.
All right. And in the work solutions, I've actually sketched that graph in the work solutions just to show you where that come from. All right.
Yeah.
Okay, that'll do us for this week, won't it?
Yeah. Be with that.
I'll see you all next week, all being well.
Yeah.
Yes.
Yeah. Take care.
Yeah. Cheers. When are you next in,
See you next
Callum?
week.
What?
Are you in on overtime at all over the weekend?
No, I'm off for 2 weeks.
No, look at you, lazy bastard. Right.
What about?